Hello everyone, welcome to another session of Virtual Academic Training Series MBD. I'm Prakash. We'll have a quick recap on what we have learned from previous session of Multi-Body Dynamics Virtual Academic Training Series. So in the last series we discussed what is a multi-body dynamics or what is a multi-body system. What are the degrees of freedom, motion of mechanics, how it is defined, and what is kinematic and dynamic behavior of mechanisms. So a multi-body system or a multi-body dynamic is defined as the study of dynamics of a system a system of interconnected bodies, and these interconnections are due to the constraints or joints. So a mechanism, it consists of a set of links connected through constraints or also called as joints with each other to perform a specified action or a mechanism under the application of force or motion. And we also discussed what is degrees of freedom. So I have a simple mechanism here. I have force on it, I have bodies, I have a global reference frame, I have local reference frames, I have a motion, as you can see, I have constraints or joints. So this all together makes a multi-body system. How can we build multi-body systems in using MotionView and run the same in MotionSolve? We can do that using interactive model building or via graphic user interface using MotionView, and one is using automated model generations using model wizards, libraries, or carrying port or TCLs. We can use MDL or model definition language or code modeling language to write a MDL file. Now in this session we will build a simple model, a simple 4-bar mechanism using a graphic user interface, which is MotionView, and we'll understand what are all we need and how a model can be built from scratch. So this is a 4-bar mechanism which we are going to build in MotionView, and these are the entities that are used to build the model. They are points, bodies, joints, motion, output request if required, units, model units, and gravity. So points, as we discussed earlier, they are the coordinate locations. Bodies includes mass, inertia, and center of gravity location. Joints, different types of joints we have revolute, ball joints, cylindrical joints, translation joints, etc. We discussed about this in earlier session. We have different types of motion, and output request is the information we are requesting from the solver, like it can be forces, displacement, joint forces, displacement, velocity, acceleration, it could be anything. And model units, you can set the model units. For example, for SI units, you can set a different model unit, and for MKS and for other systems, you can have different model units. You can change the gravity within the same MotionView, and they have some other solver parameters. Let's now start building the model using MotionView. So here I have a new session of MotionView. This is how it looks. Is the graphic. This is the graphic area, this is a project browser, and you have other panels here. We have icons and some other icons over here, and we have some icons here, image capturing toolbars, angle toolbars, and we have some other toolbars over here. This is the model which we are going to build now. So as I said, we need points, bodies, graphics. We need some explicit graphics to see the animation and to see how it works, and we need joints. and we need motion, etc. Here are the points we have. Now let's start with building the points. So basically we have three bodies other than ground body. We also have a ground body, global coordinate system over here. You can see here. So we need 4 points, 1, 2, 3, 4 points at the beginning to build the model. So what I'll do is I'll create 4 points. You can create points in either by right-clicking on the points icon over here, or you can directly go to project browser, right-click on points, and you can add points from here. Or you can also click on the model, add entity, reference entities, and points. So I'll create 4 points. 1, 2, 3, 4. I have the points over here. I need coordinates. These are the coordinate locations or the point locations. So from here I'll take the location. 0.0 is 0. I'll fit the screen for better visualization over here. And these are the points. Point 0, point 1, point 2, and point 3. Now bodies start and end on these points. Now we need to define CG locations. One way is to create points for them, or there is another way you can take advantage of the macros. All you have to do is so basically what I need to do is I need a point between these 2 points, and one more in between these 2 points. So I can take advantage of these macros, and I can create points between these points. All I need to do is I have to select the first point and the second point. I create. So this creates points in between 2 points. And you can select how many number of points you need here or here, or between any 2 points. So now I have 3, 4, 5, 6, 7 points. Now I need to build bodies. I have to create bodies. I can create by right-clicking on bodies icon, or I can use right-click on model, add reference entities, or right-click on bodies and add body. So I need 3 bodies now. 1, 2, 3. Two and 3. Now I have to give properties, mass and inertia properties. Let's assume these are the properties for body 1. And let's define its CG location. Go to CM coordinates and define the point. So now this is the CG location for center of mass location for body 1. Do the same for body 2 and body 3. So the point, give the properties. It is recommended to use correct inertia and mass properties. For the time being, I'm using, for demo purpose, I'm using some random mass and inertia properties, but it is usually recommended to use right mass and inertia properties, and also CG locations. Now I have points, bodies. Now I have to create joints in motion. Before that, we'll create some explicit graphics for a better visualization. You can either create graphics either from project browser, or you can right click on graphics icon. So I need 3 graphics for 3 bodies. So this is my parent body, this is where it starts and this is where it ends. I can provide the radius. Similarly, I'll do the same for all other graphics which I've created. So I'm creating cylinders, 3 cylinders for 3 bodies. You can also create whatever you want. You can create boxes or tubes, spring, etc. Now I'll create joints. You can create joints either from project browser or from these toolbars. Now first I'll create revolute joints. I need 1, 2, 3, 4 joints. 2, 3, 4 joints. I have 4 joints over here. Now this joint connects this body and ground body over here. And this is the point of origin for the revolute joint, and I'll align this around y-axis. Similarly, I'll do the same for remaining 3 joints. Now for second joint, I've used these 2 bodies, and this is the point where my joint goes. The last one connects ground body and the last body too over here. Now I have a multi-body system. Without joints, it's just rigid body. It's set of rigid bodies. Now I have joints that connects these bodies and makes it a mechanism. Now you can see I have bodies over here and joints connected. I'll go to check model to see if there are any redundancies. You can activate all these, so you can see what are the degrees of freedom and how many joints you have, how many rigid bodies you have over here using this. So here you can see the number of non-ground bodies. I have 3 bodies of the ground body, and the number of degrees of freedom for all these bodies is 3 into 6, which is 18. Number of joints, degrees of freedom removed by joints is 20. So revolute joint here, as we discussed, it removes 5 degrees of freedom and allows rotation in along one axis. So I have 20 degrees of freedom removed by all these joints. And total estimated year of not counting redundant constraints is -2. That means the body is over constrained. For a model like this, redundancy may not make a difference, but it is a good practice to choose the right joint to avoid redundancies in models. So what I'll do is instead of revolute joints, what I'll do is I'll make them one as a ball joint and the other as a cylindrical joint. Sorry. With these joints, I have the same behavior as I was, as I need, as intended. I'll have the same behavior, same mechanism. Now, if you check the model, you'll have total estimated keywords not counting redundancies is 1. Now, if you apply motion, even that degree of freedom will be, a number of degrees of freedom for the mechanism will be 0. You can go ahead and give any value over here. Set time. So it's similar to what I have over here. I have a motion defined on a joint, and have defined a value over here. Now here I have defined some other value. Okay, that's okay, but you can define the same over here if you want. You can go ahead and run the model. So I have the results. I can show you that. Or you can just run it. It may take some time, but now I'll check the model, have no errors, then I can go ahead and run the model. So you can see the job is completed. Let's see if we have any errors in this. No, we don't have any errors. Now we can animate the model. Here you can see the mechanism. So this is how we build, how you build a model multi-body system using MotionView, using bodies, points, joints, etc. And these explicit graphics which we are using, they don't really matter in the analysis, but they're only for proper visualization of the mechanism. This way you can create multi-body systems using MotionView. As I've said earlier, we have different graphics, explicit graphics. These are what we have created. We have implicit graphics, the small icons that you see like points, bodies, etc. They are implicit graphics. Explicit graphics, and we have primitive graphics like what we created, cylindrical bodies, graphics, boxes, spheres, etc. They only help in better visualization, but they do not involve in any calculation. And external graphics, we can import a CAD or FE model and we can use them for building multi-body systems. Now we'll discuss different types of analysis we can do using MotionSolve. So we have kinematic analysis, which can be performed for systems with levers equal to 0. Or now what we saw is a kinematic analysis, which has a 0 degree of freedom. And basically it gives the information about the kinematic quantities like position, velocity, acceleration, etc. So as you have seen earlier, the four-bar mechanism, it have one DOF. Now after applying the motion, the number of DOFs is equal to 0. And we have static analysis performed for systems having DOF more than 1 or equal to 1. So systems at rest are having constant velocity. They come under static analysis. Such systems come under static analysis, and they give information about the equilibrium forces. And you also have quasi-static analysis, which is similar to a sequence of static analysis. It is also performed for systems which has DOF more than or equal to 1. For this, you have to specify time-dependent force or motion for your multi-body model. And you have dynamic analysis. It takes into account of inertia forces, body properties, etc. So redundant constraints, as we discussed. So it is the total degree of freedom of DOF of a model. It can be calculated using number of non-ground bodies multiplied by 6 minus degrees of freedom constraint. A negative value from above equation indicates over-constrained or redundant model. So for simple models, the good part with MotionSolve is it will automatically remove any redundancies. But if you have any huge models, complex models, it is better you use proper joints to constrain your model. As we have seen earlier, for the model, these are the constraints. This is the DOF for the four-bar model. So what we had is an over-constrained model.